So today I'm talking about computational trade-offs of biological neural networks. And specifically, I'm focusing on this winner-takes-all problem, which is a famous problem in computational neuroscience. This is joint work with Nancy Lynch and Marav Potter. So our high-level goal is very broad. We're trying to just understand how computational is performed in biological neural networks, and specifically things like the human brain. And the way that we're doing this is we're basically defining network models or circuit models that are based on some biologically plausible features. So we're modeling neurons as noisy threshold gates that basically receive some input. And when they're more excited, they're more likely to fire. And then when they're less excited, they're less likely to fire. And so they're firing at any given time. And so they're basically communicating by spikes between these neurons. And we're looking at networks that have various restricted connectivity structures and edge weights that are at least loosely inspired by biological constraints. And then what we're doing with these neural network models is we're trying to understand how you can solve relatively simple problems in these models, like very foundational problems. Like the winner-takes-all problem is basically given a single neuron, given a group of neurons, I want to select the single neuron that is firing with the strongest signal. Or I want to test equality of input patterns or closeness of input patterns. So these very basic computational primitives. This is like pretty in contrast to how you usually see neural networks used in computer science. So I think neural networks usually, the first thing you think is learning. How can I use it as a platform for doing pattern recognition or classification? How can I evolve the weights on my neural network so it computes some function that I train it to compute? So while we're eventually interested in learning, at least in this talk, I'm talking about fixing the network structure and having it compute a very simple computational task as efficiently as possible. So I'm not really talking about learning or pattern recognition. So why are we looking at neural networks from this perspective? Basically, we want to understand, first of all, how do these biological features like the noise in the network or the fact that communication is through spikes and things like that, how do they affect computability, runtime trade-offs, and algorithm design? Are there like certain algorithmic patterns that you see over and over again due to the constraints of these networks? And the other big question that we have is there interesting theory for these types of networks beyond what is already known for really well-studied models of computation? Things like deterministic threshold circuits or Boltzmann machines or distributed networks with message passing, all things that can loosely at least model neural networks. We want to know if there's interesting theory there beyond what's already known here. And then finally, can this theory say anything interesting about computation in real-world networks? So our conjecture is that the answer to all of these questions is yes, and this paper is sort of our first attempt to try to show this. OK, so what model are we actually looking at? So the model we're looking at, we're calling stochastic spiking neural networks. Basically, we're looking at discrete time computation in rounds. And at each round, each neuron in the network is either spiking or it's not spiking. So we say neuron V, if it's spiking, we denote VT as 1, and otherwise we denote it as 0. Now, how do you determine whether a neuron spikes? Every neuron has some incoming synapses and some outgoing synapses. And it receives signals along those incoming synapses that induce it to spike or not spike. So what you do is at round T, you can compute a potential for that neuron, which is just the sum over all of its firing neighbors of the weight of the incoming synapse. And these weights can be either positive, meaning they're excitatory, they excite you and increase your potential, or inhibitory, negative, which would mean they're inhibitory. Now, once you have this potential, it induces a firing probability in the next round. Oh, sorry. Also, each neuron has a bias, which is sort of like whether it's more inclined to fire or not, how high its potential needs to be. So once you have such a potential, this induces a firing probability in the next round. So basically, the probability that you fire in the next round is given by applying a sigmoid function to your potential. And so as the potential gets higher, you approach probability 1 of firing. As the potential is very negative, you approach probability 0 of firing. So this is sort of where the randomness in the model comes in. You can think about it as being just inherent in the fact that there's noise in real neurons. There's just noise in how they detect when they fire, depending on what chemical concentrations they have from their neighbors. OK, another restriction we're looking at is all neurons are going to be either inhibitory or excited. Yep.
Random firings are assumed to be independent across neurons and across time.
Yeah, so yeah, every time, yeah, so your probability of firing, and then you just flip a coin with that probability. So it's independent across neurons, independent across time. Who knows if that's realistic, but this is what it is. OK, and then so we also restrict our structure in one way, which is that each neuron is either all inhibitory or all excitatory. So this is what neurons look like in nature. All your outgoing edges are either excitatory edges, you induce your neighbors to also fire, or they're inhibitory edges, you sort of suppress firing within your neighborhood. And we're going to try to look at sort of the difference between inhibitory and excitatory neurons and how they're used in computation. We ignored tons of other biological features, things like refractory period, where once you fire, you have to wait a certain amount of time to fire again, asynchrony, memory. There's all sorts of things we ignore. Some can sort of be simulated in our model, and we're beginning to understand how they might work. But it's obviously a question for future work is how do these affect things? OK, so we're going to probe our model with a really central problem in computational neuroscience, which is WTA, or winner takes all. In our case, we're looking at like the simplest version, which is binary WTA. You basically have a bunch of input neurons, and each one is either on or off. So it either fires in every round, or it doesn't fire at all. And you want to converge to a single firing output, which corresponds to a firing input. So you can think of this as like a neural leader election circuit. You have a bunch of firing inputs. Maybe they correspond to different stimuli, and you want to pick one that you want to then focus on. In the non-binary case, which is the more common case, we're just doing the binary case because it's simpler. It's sort of like a neural max function. You usually want to pick the input neuron that has the highest or the near highest firing rate. So this is very heavily studied for things like perceptual attention, so choosing between inputs, competitive learning, where you're sort of choosing between classifiers depending on how they perform on a certain set of inputs. And there's been some work in theoretical computer science on it showing that, for example, if you allow yourself like black box WTA gates and you combine them with perceptron neurons, you can do computations with many less neurons than you would if you just had perceptrons. OK, so that's WTA problem. In order to sort of facilitate our studies, we're going to look at a relatively simple connectivity structure for a WTA circuit. What this structure is going to look like is you're going to have your input neurons connected to your output neurons. So they can excite the output. Well, they can do whatever they want. We're just saying they can be connected to the output neurons. And then you're going to have a set of auxiliary neurons. In our case, we're going to assume they're all inhibitors. This assumption doesn't really matter. We can generalize. But for now, we're going to think of them as all being inhibitory neurons. An important restriction is they're not going to be connected to each other. So we're going to allow arbitrary connections to the output neurons, but not between the inhibitors themselves. And then finally, the connections to the output neurons are going to be symmetric. So all the output neurons are sort of treated equally. You're not just like, you never really favor one output over another. Some of these restrictions, it just simplifies the problem we're looking at. I'm not claiming that they're all necessarily like totally biologically motivated, but it allows us to probe at least one subset of, these are sort of a very common structure for WTA circuits, at least looked at in computational neuroscience. I also allow the output neurons, or any neuron really actually, to have self-loops so they can excite themselves and sort of have positive feedback. So how generally, this is just the model. You can then design any algorithm you want on top of it by fixing the weights of this model. But generally what's going to happen is the inputs are going to excite the outputs. If there's a lot of firing inputs, a lot of outputs are going to fire. And the role of the inhibitors is to sort of facilitate competition between these guys. So when the inhibitors get excited, they're going to sort of quiet down firing of the outputs until you get like one single firing output, which is going to be the winner. The simplest case of that we can look at is when there's two inhibitors. I'm sort of running out of time, so I'm going to go like kind of fast through this. But you're going to have one inhibitor, which is a stability inhibitor, which fires whenever at least one output fires in the previous round. This is going to ensure that once you converge to a winner-take-all situation where there's one firing output, that output's going to have a self-loop, and it's going to remain excited and continue firing, while all the outputs, there's enough inhibition to keep all the other outputs quiet if there's this inhibitor firing. You're then going to have a convergence inhibitor that fires when there's at least two firing outputs. And this is going to increase the level of inhibition to the point where even outputs that fired in the previous round are going to only fire with probability 1/2 in the next round. So basically, roughly half of the competing outputs are going to stop firing in every round, and you're going to get convergence in log n rounds. This is like, yeah, again, I'm running out of time, so I'm going very fast, but this is sort of the most basic WTA circuit. And we show a bunch of generalizations of this circuit where we increase the number of inhibitors and have more refined behavior of the firing probabilities. We get upper bounds by basically generalizing that circuit, and then lower bounds by sort of indistinguishability argument, showing that the circuit will not behave differently on different classes of input, and therefore can't solve the problem for both. But I think the main upshot is that our lower bounds sort of match our upper bounds, and that they show that some features of our upper bounds are inherent to optimal circuits. So one is this division into convergence and stability neurons is sort of inherent. In any near optimal WTA, you have some inhibitors that have to fire once you've converged, and you have some that sort of drive the computation. And inhibition is often viewed as like a stability mechanism in the brain. And what we're showing is this sort of dual nature of it's a stability mechanism and then also it's driving computation of these circuits. The second feature that we see, yeah, I'll do this to the last thing, is that basically inhibitors behave nearly deterministically in any near optimal circuit. So this is sort of showing this duality of randomness. So the randomness is inherent in WTA. If you don't have it, you can't break symmetry between the inputs. But the more noisy the inhibitors behave, the slower your runtime becomes. And so in this case, you're paying for the randomness. So it's a sort of trade-off that you have. So I'm out of time, so that's pretty much it. There are some open questions. I can take questions.
Any questions?
So the connection of having no self-connection between the inhibitors is realistic, technically necessary, and when
It's technically necessary, because to prove our lower bounds, it gets really complex if they have connections between themselves. It's also sort of realistic. It's hard to say if it's realistic. So it is observed that in the brain, there are many less inhibitors. They tend to be in like much simplified connectivity structures. And so in this sense, there's this vague sense that they're doing some sort of like general, is having sort of a similar effect on all their neighbors rather than like some very complicated interaction there. But it's not, yeah, I can't claim that that's actually so, yeah.
But in the brain, there is evidence that certain parts of the brains really is a directed graph. A certain layer talks to another layer, right?
Right.
And sometimes there are very mostly no connection on the same layer. So
Right.
do we know that these inhibitors actually lie on a layer?
I'm not sure. Yeah, I'm not sure.
Any other questions? Thank the speaker again.